Have you noticed how salt dissolves easily in water, but oil doesn't? Or how carbonated drinks lose their fizz when left open? These everyday observations are governed by the concept of solubility, how much of a substance can dissolve in a given solvent under specific conditions. In this lesson, we'll explore what solubility is, how it varies for liquids, solids, and gases, and we'll understand two critical laws that describe this behavior, Henry's law and Raoult's law. Solubility is defined as the maximum amount of solute that can dissolve in a specified amount of solvent at a given temperature and pressure to form a stable solution. It is a quantitative measure and it differs from substance to substance and solvent to solvent. Solubility depends on nature of solute and solvent temperature pressure. In case of gases, remember, like dissolves like. Polar solutes dissolve in polar solvents and non-polar solutes in non-polar solvents. When two liquids mix to form a homogeneous solution, their solubility is assessed based on their miscibility. Completely miscible liquids mix in all proportions, example ethanol and water. Partially miscible liquids mix only in certain proportions, example phenol and water. Immiscible liquids do not mix, example oil and water. The key factor is intermolecular interactions. If the interactions between solute and solvent molecules are comparable to those within each pure liquid, solubility is high. For solids dissolving in liquids, three factors influence solubility: nature of solute and solvent. Ionic and polar solids dissolve well in polar solvents. Temperature. For endothermic dissolutions, delta H is less than 0, dH greater than 0. That is, the dissolution is exothermic, solubility increases with temperature. For exothermic, delta H is greater than 0, dH less than 0. It decreases, that is, the dissolution is endothermic. Dynamic equilibrium, when rate of dissolution equals rate of crystallization. Solute, solid, plus solvent is in equilibrium with the solution. Example: sugar dissolves in water. More dissolves when water is heated. Gases also dissolve in liquids, and their solubility is influenced by temperature. Solubility decreases as temperature increases. Dissolution of gas is an exothermic process. Pressure. Higher pressure increases gas solubility. You've seen this in soda bottles. When sealed, they are under pressure. Once opened, pressure drops and CO2 escapes. The fizz disappears. To quantify this relationship, we use Henry's law. Henry's law states that the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas above the liquid. Mathematically, P equals Kh multiplied by X, where P is the partial pressure of the gas, X is the mole fraction of the gas in solution, Kh is the Henry's law constant. Example from NCERT. If nitrogen exerts a partial pressure of 0.987 bar and Henry's constant for nitrogen at 293 Kelvin is 76.48 kilobar, the mole fraction is X equals 0.987 divided by 76.48 multiplied by 10 to the power 3 equals X equals 1.29 multiplied by 10 to the power minus 5X equals 0.987 divided by 76.48 times 10 to the power 3 equals 1.29 times 10 to the power minus 5. The higher the value of Kh, the lower the solubility. Soft drinks are bottled under high pressure to increase CO2 solubility. Scuba divers breathe compressed air. As pressure increases underwater, more nitrogen dissolves in their blood. Rapid ascent leads to nitrogen bubble formation, causing bends. At high altitudes, lower oxygen pressure leads to lower oxygen solubility in blood, a condition known as anoxia. Henry's law is essential in biological systems and industrial gas applications. Let's now talk about Raoult's law, which relates to vapor pressure in liquid solutions. Raoult's law states that the partial vapor pressure of each component in a solution is directly proportional to its mole fraction. For a binary liquid solution, P1 equals X1 multiplied by P1 naught and P2 equals X2 multiplied by P2 naught, where P1 and P2 are the partial pressures, X1 and X2 are the mole fractions, P1 naught and P2 naught are vapor pressures of pure components. Total vapor pressure. Total equals P1 plus P2, which equals X1 multiplied by P1 naught plus X2 multiplied by P2 naught. This law is the basis for understanding ideal solutions and non-ideal deviations. Let's recap what we've learned. Solubility is the ability of a solute to dissolve in a solvent. It varies for liquids, solids, and gases based on interactions, temperature, and pressure. Henry's law explains gas solubility and its dependence on pressure. Raoult's law governs vapor pressure in liquid solutions using mole fraction.